Teaching algorithms how to actually cooperate with one another, honestly, sounds a bit like science fiction, but it's actually a very real, incredibly complex mathematical problem. Welcome to This Explainer. Today, we are unpacking a truly groundbreaking paper titled Regret Minimization with Adaptive Opponents in Repeated Games. This comes from a powerhouse team of researchers at MIT, OpenAI, and the University of Maryland. The core dilemma they're tackling here is fascinating. How do you train an AI agent to anticipate the future reactions of an opponent who is also adapting and learning? We can't just treat every interaction like it exists in a vacuum anymore. So we're going to look at how we measure algorithmic regret, why the old ways of doing it are completely failing us, and how a brand new mathematical framework is paving the way for multi-agent systems to literally learn the math of trust and cooperation.
Here's our roadmap for this explainer. We'll establish the baseline with the game theory problem and why standard regret fails. Then, we'll introduce the solution, repeated policy regret, and the power of forgetting, before diving into the hard data with the stag hunt and what this all means for the future of cooperation. All right, Section 1, the game theory problem, the limits of pure logic.
To truly get what's happening at the cutting edge of AI, we gotta take a quick step back into classical game theory, which is essentially the mathematical study of interactive decision-making. Historically, algorithms have really struggled when decisions aren't just a simple one-off choice, but part of a long-term dynamic relationship. And that brings us to the concept of repeated games. A repeated game is exactly what it sounds like, a game where the same exact players interact continuously over time. Now, this is a massive paradigm shift. Think about it. In a one-shot game, you just make the best logical choice in that single isolated moment. But in a repeated game, players can adapt based on the entire history of play. Your actions today are going to provoke a reaction tomorrow. It's an ongoing relationship. And as you'll see, algorithms trained for isolated events completely fall flat on their faces when you put them into a relationship.
Let's look at the classic iterated prisoner's dilemma matrix. It's the perfect way to see this trap in action. There's this severe, constant tension between mutual benefit and selfish temptation. Look at the top left. If both algorithms cooperate, they both get a pretty solid utility of 0.6. But if one cooperates and the other defects, look at the top right and bottom left, the defector gets a massive 1.0 utility, leaving the poor cooperator with absolutely nothing, a 0.0. Because both algorithmic players logically want that sweet 1.0 and they're both terrified of getting 0.0, they are heavily, heavily tempted to just defect. And if they both do, well, look at the bottom right. They end up in the defect-defect loop, getting a dismal 0.2 each. Now, humans can sometimes escape this trap by building trust over repeated interactions using strategies like tit for tat. But how on earth do we teach an algorithm to see that? Moving on to Section 2, why standard regret fails, the stubborn AI.
So, for years, we've trained algorithms using a very specific performance metric to evaluate how well they're doing. But it has a fatal flaw when it comes to these repeated interactions. That metric is called external regret. External regret basically measures how much an algorithm regrets its past decisions compared to a static, fixed strategy it could have played instead. Think of it like a stubbornly rigid AI that just refuses to read the room. It implicitly assumes the opponent is non-adaptive. It evaluates its choices assuming that, hey, if I had done something differently in the past, my opponent would have still played the exact same sequence of moves. But in a repeated game, that is totally false. If you deviate, your opponent reacts. External regret completely ignores this counterfactual reality.
And because of that exact blindness, minimizing external regret in the iterated prisoner's dilemma forces both algorithmic players straight into that relentless defect-defect loop we just looked at. Even if you program a brilliant cooperative strategy, an algorithm using external regret will look back and say, man, if I just defected while my opponent cooperated, I would have scored a 1.0. It doesn't realize that defecting would have completely broken the trust and ruined all its future payoffs. So it simply learns to defect, dragging the utility down to a miserable 0.2. It completely, utterly fails to find the cooperative equilibrium. Section 3. Repeated policy regret explained, a game theoretic metric. So here is the brilliant solution the researchers propose. Teaching the algorithm how to actually do counterfactual reasoning by having it ask, if I had changed my policy, how would my opponent have adapted? The contrast here is super clear. While external regret assumes static, unresponsive opponents, this new metric, repeated policy regret, or RP regret, explicitly accounts for adaptive opponents responding to the history of play. Under RP regret, the algorithm finally understands that a deviation today ripples outward. It affects the distribution of histories, which in turn alters the opponent's subsequent play. RP regret measures the difference between the realized utility and the best in hindsight accumulated utility when all players can respond to the history. Honestly, it's a massive leap forward in multi-agent learning. But, there's always a catch. Minimizing RP regret is mathematically incredibly tricky. It's highly non-convex. The researchers identified that for an algorithm to successfully minimize RP regret sublinearly, which basically means it actually learns and improves over time, certain strict mathematical conditions have to be met by both the AI and its opponents. First, condition 1, sublinear variation. This just means strategies have to change relatively slowly. If the target strategy you're comparing against behaves completely erratically, you can never learn to match it. Second, condition 2, imperfect recall. The algorithm cannot perfectly differentiate every single history it has ever seen. And most importantly, condition 3, exponential decay memory. So what exactly is exponential decay memory? To put it in human terms, algorithms shouldn't hold a grudge forever. Mathematically, it bounds how sensitive a strategy is to the distant past. If you and your opponent share the same recent history, altering something that happened way back at the very beginning of the game should have an exponentially decreasing impact on your current decision. Without this condition, an opponent could use a single action on day one as an information carrier to encode some secret protocol, essentially preventing the AI from ever successfully learning the environment. For cooperation to mathematically work, algorithms, much like us humans, have to learn to forgive and forget the distant past.
Which brings us to Section 4, the power of forgetting, engineering LRP regret.
All right, let's really break down this tree diagram because it beautifully illustrates how the researchers solved a massive problem, the exploding state space. If you try to track every single interaction in a repeated game, your state space, the sheer number of possibilities the algorithm has to compute, blows up exponentially as time goes on. It becomes literally impossible to calculate. So the researchers reformulate the repeated game as a Markov game using bounded memory. Look at the left side of the visual, the part marked I. We see a tree structure representing histories. Notice that red curved arrow pointing from a yellow node back up to another yellow node on the right side of the dotted line? That illustrates how under their specific mathematical constraint, the maximum depth of the tree representing the game state remains bounded at a depth of 3. The algorithm doesn't need to build the tree infinitely downward. Now compare that to the right side of the visual, marked II. You see a green node added at the top, and the red lines show the tree expanding downwards, increasing the maximum depth from 3 to 4. What this diagram proves visually is a vital mathematical lemma in the paper. By enforcing that exponential decay memory condition we just talked about, you can effectively truncate an unbounded, infinite history into a manageable, bounded, M-length history with only a tiny, exponentially decreasing error margin. The state space stops blowing up. This tree visualization is the exact mechanism that proves we can turn an intractable, infinite memory problem into a solvable Markov state problem, all without losing the essence of the adaptive opponent. So, how do we actually pull this off? The paper proposes 3 algorithmic pathways to mathematically conquer the non-convex challenge of RP regret. Pathway 1 is mostly theoretical. It assumes a magical optimization oracle. Pathway 3 is what we just looked at, reformulating the whole thing as a Markov game in the space of occupancy measures, which works wonderfully if opponents change slowly. But Pathway 2 is where the practical magic really happens, minimizing a convex linearized surrogate called LRP regret. LRP regret stands for local repeated policy regret. Instead of comparing the algorithm's entire lifetime of choices against a global alternative, which is mathematically chaotic, it applies the one-step deviation principle. It basically asks, hey, if I only locally deviated from my strategy at one specific time step, would my average loss over time decrease? By linearizing the expected loss locally around the strategies currently being implemented, the problem suddenly becomes convex. And once it's convex, algorithms can use standard, highly efficient tools like projected gradient descent to adjust their cooperative strategies locally, step by step. It's a real game changer. Section 5, winning the stag hunt, visualizing the payoff. The researchers didn't just prove all this on paper. They ran simulations to see if LRP regret actually fosters cooperation in practice. To test it, they used the classic stag hunt game. Imagine 2 hunters. They can either hunt a stag together or a hare individually. If they both hunt the stag, they get a massive 1.0 utility each. That is the global optimum. But a stag requires 2 people to take down. If you commit to hunting the stag and your partner gets distracted and hunts a hare instead, you get a measly 0.1, and they get an easy 0.8. If you both just play it safe and hunt the hare, you both get a safe 0.5. The stag hunt requires absolute, unwavering trust. In traditional learning with external regret, algorithms often panic, take the safe route, and settle for the hare, locking themselves into that mediocre 0.5 outcome.
Now look at this bar chart. This is the hard data. We are looking at the average utility across 10,000 runs of the stag hunt game over 100,000 iterations. On the y-axis, we have the average utility, climbing from 0.5 up to 0.75. On the x-axis, we have the memory length, denoted as m. The very first bar on the left is standard projected gradient descent, essentially the baseline without our new memory mechanics. Notice how it sits way down below 0.6? That means the algorithms frequently failed to trust each other and settled for the hare. But as we move to the right, we apply LRP regret minimization with increasing bounded memory lengths. Look at that jump. At memory length 1, the utility jumps up to nearly 0.65. At memory length 2, it surges to almost 0.7, and at memory length 3, that bar on the far right, it pushes past 0.7, getting closer and closer to that optimal stag-stag payoff. This graph is the definitive proof of the paper's thesis. As you give the algorithm a longer but still bounded and decaying memory to track counterfactuals, minimizing LRP regret successfully guides the multi-agent system away from the selfish trap and directly towards the optimal cooperative equilibrium, far, far better than standard methods.
That perfect 1.0 utility of stag-stag, that is the absolute holy grail here. By minimizing LRP regret, these algorithms genuinely learn to anticipate the opponent's reactions. They realize that if they defect to hunt the hare today, the opponent will see it and stop trusting them tomorrow. They actually learn the math of trust, proving that algorithmic cooperation is not only possible, it is entirely computable.
Section 6. The future of cooperation. Equilibrium computation.
The implications of these findings go so far beyond a simple matrix game. They fundamentally advance algorithmic game theory. Here are the key technical triumphs of the paper. First, RP regret allows for dynamic, time-varying comparators, meaning the AI isn't forced to evaluate itself against a rigid, static benchmark anymore. Second, through tools like LRP regret and bounded Markov states, it retains computational tractability. It's not going to crash your server. And third, it enables the computation of incredibly complex equilibria, specifically subgame-perfect coarse-correlated equilibria, or SPCCE. In plain English, minimizing this specific type of regret leads algorithms straight to robust, cooperative states that older methods literally cannot find. The researchers themselves put it perfectly. Minimizing our regret notions can lead to more cooperative solutions with higher utility in games such as Stag Hunt. At the core of all these dense, non-convex optimizations, occupancy measures, and gradient descents is a profound breakthrough in achieving mutually beneficial outcomes. I want to leave you with this final thought today. If we can mathematically engineer algorithms to use RP regret, to essentially learn the mechanics of cooperation, foresight, and even a mathematical form of forgiveness by decaying past grudges, what does that mean for the future of multi-agent AI? As our systems become increasingly autonomous and interconnected, teaching them the value of the stag over the hare might just be the most important computation of all. Thank you so much for joining me for this explainer. I hope this helped unpack the fascinating math of algorithmic cooperation.